Hi, so we are at our last and final big data's group assignment. So this time around, we will be trying to predict the race win based out of Formula One data set. So our reference today will be the Formula One website. So we had access to the Formula One's race results data and also the final data. We just had to compile together all the race win weather data and constructors and qualifying results, like everything. So we won't be using everything, but we will be using many of those columns to predict our race winners. So this is a classification problem, and we will only be predicting who will be winning the race. We won't be predicting the the final position of each and every racer once a race starts. So this is not that kind of prediction, because race dynamics always change, and one big object is the initial grid position towards the start of the race, and most drivers tend to keep that grid position. So this is how it goes. So let's jump right into the data set. So we have the f1.csv that we are importing, and so inside the Formula One data we have 37 seasons, and we have 14,273 races, which translate to 14,273 records, and we have 226 drivers, and so we have just visualized the number of race wins for each driver, and we have visualized the number of incidents per location before going there. So we are using the race results.csv. Remember, race results.csv won't be used for our model. These are just interesting stats that we thought would be helpful in summarizing how we compile together the final result set. So they say 1K is toughest circuit, and because it has a lot of incidents in it, and Ferrari has the most number of accidents involved, and Alonso, for the past from 2015, Alonso has been involved in a lot of incidents. And before we head into the correlation matrix, I want to let you know that there are factors which affect the final prediction. So it's not always so. According to our correlation matrix, so when we get into the correlation matrix, we can see that the initial grid position has 50% chance of has a 50% chance of affecting the data set. It means the person who ends up winning the qualifier also ends up winning the race, which translates 50%, more than 50% of chance of the times this is the case. And there are other factors like accidents on the track and overtakings and stuff like that, abnormal pit stops and all that affecting the final prediction. So that is what the correlation matrix explains, and the logistic regression model will be taken over by Mandar. So there will also be other factors. So there will be overtakes, and there will be pit stops. So ideally the pit stop usually takes 2 to 5 seconds for a car. So there will be issues going on with pit stops, and there would be instances where cars stop for more than 10 to 15 seconds and maybe also exit the race. So which happened in the recent Grand Prix, if you follow it. So pit stops have a lot of impact on how the race goes. So, and also drivers with the most failures in the recent times. We have failures in the recent times. Failure means, by failure I mean incidents on the racetrack. So we are focusing on Grand Prix greater than 2015. So we are not going all the way back to 1950 for this particular chart. So this is how the list goes. And looking into the schema, we have all of those. We had to manually change the data types from within the data bricks, and so most of these were not all of them showed up as string when we tried to upload them. So we had to manually change each and every column's data type. So once we have the data type So I tried to create a correlation matrix. So this is the template we will be going with further into this model. So we will be using drivers. Right, since driver is string, we'll have to use a string indexer and use it along with the vector assembler. So once we have the assembler code, so we have the input columns, the index driver, the season, round, grid, driver age, and podium. So once we have this, we are creating a pipeline to run the string indexer first and then the assembler. So once the pipeline has been, a template for the pipeline has been set up, we will be fitting the data frame within the pipeline, and then we will extract once the data frame is transformed using the pipeline, we will be extracting the correlation matrix, and we will be using the regular matplot library for the correlation. So as you can see, the podium is explained the greatest by the grid position. So initial grid position has a lot to do with the match final result, and upcoming the logistic regression model and also the random forest classifier will be explained by Mandar.
Hi, and thank you, Sai. So I'm gonna explain the building the logistic regression model. So basically what we've done is we've dropped all these columns from our data set because we feel that these are not important from the point of view of our prediction as of now. And also all these columns bring noise to the data set. So we've divided the data set into train test split with training data is 70% and testing data is 30%. Then we've changed the driver indexer, which is changing the driver name to numeric column. And then we've passed it through an assembler where other features come with the driver indexer. We've run this through the pipeline and fitted the model. After that, we've got the logistic regression label column podium. So what I'm going to do is explain podium quickly. Podium is the amount of finishes that the driver has in which he wins the race. So basically that's a podium finish. So if suppose podium is equal to 0, so that means that the driver did not finish on the podium. That is, he did not win the race. So yeah, then what we had is our features and podium fitted trained into this thing and fit on the model. After that, I'll tell you that we did transformation on test data and then fit the data on test. And here are the results, and we've done raw prediction, and probability. So I'm going to explain what we did here. So this is actual podium finishes. This is the prediction. This is the raw prediction. This is the prediction again, and the probability. So this is for comparison over here, and this is what the probability does is it tells you, it actually backs up our prediction, which is that we made, and tells us by what percentage does that thing actually happen. So what I'm saying is podium, which is equal to 0, has a prediction of 0. That means that the driver did not win the race, and he actually did not win the race, and the probability of this prediction being true is 0.99. Other than that, we can see that our test accuracy is 0.92, which says that 92% of the time our classification is true. It means that 92% of the time we predicted a podium finish as a podium finish and a podium not finish as a podium not finish. Yep. We'll move to the next algorithm, which is random forest classifier. We've imported all the necessary uh, libraries over here, and we've done the train test split with the same drill as we did. We converted the driver column into numerical, and then we sent it to an assembler, and over the assembler then we passed it to the pipeline. We fit the train data and transform the train data. And then what we have over here is we bought the model for random forest. So what it does is it takes features that is explained in the above steps, and it has number of trees is 10. So imagine 10 different trees with bins, and these trees predict each of the data amongst themselves, and after that we get an aggregated view of the result. So it's basically taking all of the results and doing a voting classifier, or we can do any algorithm other than that as well. For this also we got predictions on podium finish. Suppose the driver actually finishes 0 and the prediction is 0, our prediction also is 0 for this, and the probability is 99% that what we've predicted is true. The accuracy for this model is 93%, which is good enough, and the next models will be explained by Vamshi. Thank you.
Thank you, Mandar, for explanation of the modules random forest classifier and linear regression model. And here I am going to explain about the models, other two models. Those are SVM classifier and multi-perceptron classifier. So this is basically SVM classifier and multi-perceptron classifier, or the classification binary classification problems. And here we are basically importing the libraries from here, and then we are splitting the data based on that by using of the train test data random split. And the string indexer is something like which maps the string column of labels to the machine learning column of labels, and it will prioritize the maximum frequency of the input columns in the top. And then this vector assembler is used to create the vector of the input features, like whichever of the input columns we are giving in, they will be taken as the vector of input features. And after that again this is completely pipeline. So like the pipeline has the different stages which takes the input of driver indexer, that's from here, and then assembler underscore sv. This is forming a basically one kind of input transformation matrix. And then this is fitted into a fitted pipe, and after that we are using the linear SVC library or framework, and we are giving the label column which is the prediction column as the podium, and the features column as max features, and these are the parameters in the linear SVC. And then I am fitting the model which we obtained by using of fit function, and again I am transforming the data by using of the transform function. After that the results are stored into the a data frame that is podium, prediction, draw prediction, and prediction. So here after the completion of the model I am getting the accuracy of 92% by using of the binary classification after evaluating the model's accuracy. So the loss is as accuracy minus the value of whichever we are not getting, like the accurate results is the loss, so that is the 7% loss. And almost it is same for the multi-perceptron classifier as well. So here we are using the string indexer to string column of labels to ML column of labels, and then vector assembler, and then pipeline. This is the same process, except here we are using the multi-perceptron classifier, which is the library for multi-perceptron, and these are the label column, and this is the feature column. These are the parameters into the multi-perceptron classifier. And after that we are fitting the model, and again we are transforming the model by using of the test data set, by comparing it with the trained data set fit model, and the results we are storing into the fit underscore a data frame result underscore ml. And then we are checking out these columns like podium, prediction, raw prediction, prediction, probability. And in this model we are getting the accuracy of 94%, so the test error is 5%. Thank you.
So quickly concluding what we have seen so far, we have noted that the multi-layer perceptron classifier, which is a form of neural network, performs the best with 94% accuracy. And as we have seen the correlation according to the correlation matrix, the person who starts first, qualifies first, and who takes the initial grid position always ends up winning, mostly ends up winning. And also Formula 1 also has a lot of unpredictability going on, like car failures and overtakes, so there's always a chance that our prediction can go wrong when something like this happens. And with the accuracy we have achieved, we can also use this training data set to predict future events, like 2015 to 1950 to 2019 data set we have. We can try 2022 or 2023 predictions and see how this goes. And we have also observed that there is always a homegrown advantage, which also affects our final performance. So we have so the additional race results data set helped us find this out. So yeah, thanks for listening us so far. It has been a wonderful semester. Thank you.